Hi everyone, my name is Derek Kutsia, and this is going to be a multi-part video tutorial of the Stencil specializer, which is one of the most mature and well-developed specializers that uses the Asp SEJITS framework. Now, if you recall, a specializer is essentially a mini compiler that is able to solve a certain class of problems that is expressible in Python by converting it into a low-level language and executing that compiled low-level language on the fly. So before we can talk about how the Stencil specializer is implemented, first we have to talk about what is a stencil and what is the kind of problem being solved by this specializer. So I'm going to introduce stencils and show you how they work. So for my running example, I'm going to be using this. This is a picture of a squirrel, and it's a relatively low resolution picture, but it's still very sharp. And we want to run it through a filter that's going to produce this blurry squirrel. Now, this is a very simple filter to do, actually. Each of these pixels is represented by an integer between 0 and 255, and we end up with a grid of these integers. To produce the output values, we just take each set of input values from the 4 surrounding squares and we average them. We sum them up and divide by 4. And that gives us the output value for this pixel. So, in other words, we have an input grid that looks like this, and we have an output grid of the same size. And in the output grid, this pixel is determined by the values of these 4 pixels, averaged together. Now we're going to take a look at the code and see how that's done. So we're going to start out by just writing the simplest possible Python program to do this. This doesn't use SEJITS, this doesn't use the Stencil specializer, this is just pure Python. What it does use is SciPy. SciPy is the scientific computing library for Python. We are using it because it provides a handy function, imread, which is short for image read. It allows us to provide an image file name on the command line and read it into an array. And what we're going to get here is essentially a two-dimensional array, or a matrix of values between 0 and 255, representing the gray intensity of each pixel. Then we're going to create another array of the same size. So we're passing in the shape here, the same shape as this input matrix, but it's going to be filled with zeros. This is going to be our output matrix. Next, we loop over all the pixels of the output matrix, and for each one, we examine each of the 4 surrounding pixels in the input matrix, and we divide each one by 4 and add it to the output matrix. Now, there is a subtle thing here that's important to note, which is that we're not actually looking at every single pixel of the output matrix. We're actually skipping the ones that are right next to the border of the image. And the reason is because they're not going to have an input pixel on all 4 sides. And when you actually do a blur operation, you have to worry about handling these edge cases. But for now, I'm just saying we're going to skip all those pixels and just blur the ones in the interior of the image. So we're going to end up with basically a black border around the image that's 1 pixel wide. Finally, we call scipy-misc image save, which just takes an array and saves it back out to the file. Now, there's a subtle thing here, which is that when we read these in, we get these integers between 0 and 255. And when we divide an integer by an integer, that can truncate the integer. So for example, if we did 3 divided by 4, we would get 0. And that can lead to slightly incorrect results in this computation. So the way that we deal with this, if we move on to the second version, is when we load it, we do as-type float to convert all of the integers between 0 and 255 to floating point numbers. Then these will all be floating point operations. The result will be a floating point number. And then before we can save it back out to the file, we have to convert it back to an integer, like this, out.astypeint. So that's simple enough. Now we're going to start talking about how we can refactor this to make it a little bit cleaner. So you probably noticed that this code, these 4 lines, although they're all different, they feel really repetitive. They're all adding an element of the input array divided by 4 to the output point, out yx. So one simple way that we can simplify this is to define a neighbors function. What the neighbors function is going to do is it's going to take a tuple, a point yx, and it's going to compute the points or the locations of all of the 4 neighbors and return them. So it just does p0, p1 minus 1. So if we go back here, it had yx minus 1, p0, p1 plus 1, yx plus 1, and so on. You get the idea. We return these 4 points. Then, instead of having 4 statements, we have a loop over a single statement. We just say for n, now n is going to get assigned to a tuple of an x and a y position for each of the neighbors of this point yx. Then we're just going to look up that tuple in the input array, get the value at that point, divide by 4, add it to the output point. So that already simplifies our code quite a bit. But there's actually more we can do to make our code a little bit more generalizable. The next thing we're going to look at is here, pretty much no matter what kind of operation we do on the output image, we're going to want to be looping over all of these interior points. And we don't want to always reproduce this loop. So what we're going to do is define a function here called interior points. And interior points is just going to take an array, and it's going to do those 2 loops we saw before, but instead of doing something inside the loop, it's just going to store all of the points in a list. And then once it's built up that list, it's going to return it. What that allows us to do is just say for p in interior points of the array, and now we can just get all of the xy points in a single list like this. Now, in general, this is going to be pretty inefficient because we're constructing a really big list that actually has points for every possible point in the image. You could do this with iterators and make it faster, but this is just to give you the concept of how it works. So we're looping over all of the interior points. Then we're looping over all the neighbors of each point, and we're adding each neighbor divided by 4 to the output point. So we've reduced our main kernel here to just 3 lines, and that's pretty cool. I also wanted to show a small improvement we made to neighbors. So before, neighbors had PO, P1 minus 1, PO, P1 plus 1. So this just simplifies that a bit by saying we're going to do PO plus I, P1 plus j for ij in these. So these are just simple integer sets describing the offset of each one of the neighbor points from the center point that was specified. So stencils are always going to have this kind of pattern where you have some point in the middle and the other points are specified relative to it. And the offsets from the center point are always going to be fixed. So it's okay to specify them as a list of integers like this. Okay, so we have our neighbors function, we have our interior points function. Now it turns out that one of the first things that the Stencil specializer provides is basically just a utility class that gives you these functions for free so that you don't have to write them yourself. So if I click over here, if I open up the import, you'll see that from Stencil kernel, which is one of the Stencil specializer classes, I've gone ahead and imported Stencil grid. Stencil grid contains, like I said, those 2 functions that we saw before. So we load in the input array just like before. We initialize stencil grid with the shape of the input array. It always needs to know the dimensions of the array that's going to store. And then we just assign it to the .data element of the input array. So we've gone ahead and put the data inside it. Now, instead of having a neighbors function that does this, we really only need to specify this, the list of offsets. And the way that we do that is we just say input.neighborDefinition1 equals that list of offsets. So 1 here is just a label, and that's going to come up again in a second. Then we have our output stencil grid, which has the same shape as the input array. It'll be zeroed out by default. And on the output grid, we're going to set something called the ghost depth. So ghost depth just means how wide is the border around the image. That is not part of the interior points. So because all of our all of our neighbors are just 1 pixel away, it's okay to have a border that's just 1 pixel wide. But if our neighbor list was larger and we had some points that were 2 pixels away, then we might actually want to have a border that's 2 pixels wide so that we don't go over the edge. So that's what that is. Finally, just as we had interior points before, our output matrix has an interior points method on it. We can call that to just get its interior points so that we can assign to them. And we can ask the input grid for the neighbors of a particular point. And here's that 1. This 1 corresponds to this 1. So it's the label of the neighbor definition. And we could have several neighbor definitions here if we wanted to. And we could refer to them as 1, 2, 3, and so on. Then finally, just like before, we add that each input neighbor divided by 4 to the output. We convert back to integers, and we save it. Now, this is useful for refactoring your code, but this is still running as pure Python. There's no performance advantage yet. And I want to take a quick look at just how bad the performance is with this particular program. So I'm going to start out with the image of the squirrel that I showed you earlier. Here's the squirrel image. It's not a very big image. We can zoom in on it. So there's our squirrel. Now we're going to go ahead and run it. We're going to run Python blur.py on squirrel.png, and we're going to output it to squirrelblurry.png. So that was pretty fast. If we put time in front of it, we can see how fast it was. That was about 2 seconds. So that's not too bad. And if we go over, we can see our blurry squirrel, just as desired, squirrelblurry.png. So far so good. Now over here, we have Big Squirrel. Big Squirrel is a big version of the same image. Whereas the original image was about 100 pixels wide, this image is about 800 pixels wide. So it's about 0.8 megapixels. It's by no means an enormous image. It's not unreasonable that we might want to blur this image, but it still has quite a few more pixels than the last one. So we're going to return to our console. We're going to put in Big Squirrel. Try and blur that. Now this is going to take a while, and the reason this is going to take a while is that Python is an interpreted language, and even though it seems like it should just be looping through an array, which would be very fast in a language like C++, in Python it's spending thousands of instructions examining every single pixel. And essentially what we want to do is we want to take that Python main loop that's doing all the hard work of the blurring and compile it down into C++ so that it runs as fast as possible. Then we just call it from our Python program, have it compute the answer, and return the resulting array to us. Now when we do that, it's going to have a certain startup cost because the compilation itself is going to take several seconds at least. But when we're comparing several seconds of compilation to this ridiculously long runtime on this Python program, that's small potatoes. So it should just be another few seconds. There we go. It took about 1 minute and 11 seconds. So that's 70 seconds, which is a lot longer than for the small image. And this is, remember, just an image that's 800 pixels wide. It's not really that big. It shouldn't be taking that long. So the next thing that we're going to do is we're going to look at the final modification of this program, where we are going to import everything from Stencil kernel, not just Stencil grid. And we're going to take the loop that we had before and move it into this method. So we have a new class called kernel, and it has a method called kernel inside it. It takes the input and output grids as arguments, and then it does the same loop that we had before. Then we just invoke that method from here. Now when you first look at this, you're probably thinking, well, that's just going to run the same code as before. Nothing's going to change. It's still going to be slow. But there's a little magic happening here. If you look at the base class of kernel, the base class is Stencil kernel. Stencil kernel is a special base class that's supplied by the Stencil specializer. And what it does is when you execute kernel, it intercepts the call. It examines the source code of this method. It generates C++ for it, compiles it, and then executes it on the fly. So we're going to see how that works. This is blur 6. First, we're going to try it on the small image. It's generated the C++. Now it's compiling it. Now it's just about done compiling. And it's done. So as you can see, this took quite a bit of time just to compile that source file. And that's not always going to be a worthwhile overhead, like in this case where it originally only took 2 seconds to deal with this image. But when we deal with a larger image, like the big squirrel image, it's going to do exactly the same compilation, except that it has to redo it for every image because its generated code actually depends on the dimensions of the image. Now, this should take about the same amount of time as the previous one because the C++ code runs so fast. There you go. As you can see, almost exactly the same time. And that's a lot less time than it previously took, over a minute to run. So that's the basics of the Stencil specializer. And next time I'm going to show you, start getting into the guts of the Stencil specializer, talking about what kind of constructs can you specify inside your kernel function. We're going to talk about how we formalize that language of what type of functions can go inside the Stencil specializer. And then we're going to talk about how we translate that from Python into our internal model representation. Thanks for watching, and have a good day.